So some function r of t, x, which is x of t in the direction of I and y of t in the direction of j. Direction of j in the interval from the interval a to b is smooth whenever their derivatives with respect to of both components are continuous in the interval a to b, and of course not simultaneously zero on the open interval, right? So, and it's piecewise smooth if the interval AB can be partitioned into finite number of sub-intervals, each of which is smooth. All right. So in some cases, we can have what do we mean by piecewise smooth? For example, in 2D, something simple in 2D. So we can a particle can go into a diagonal. Yes, as a diagonal, and then as a diagonal, then as a curve, then horizontally, then maybe in circular form. I mean, there's many ways a particle can travel with respect to time. However, in this case, if we wanted to evaluate an integral, or if we wanted to find some, or rather to describe this this function, we can notice over here this sharp corner, this other sharp corner, another sharp corner. That function is not defined on those, or rather its derivative, it's not defined on those sharp corners. So whenever that happens, we will have to define this function as piecewise. And in this case, this C will be C1, C2, C3, C4, C1, and it's going to be defined into different pieces. But well, before coming up with piecewise functions, let's first review how do we parameterize, for example, a linear function, a line segment from the point 251 to the point 320. All right, so number one, recall that the parameterization of a straight line, it's given by number one. We need to find a vector. Recall that back then we didn't really define a slope, you know, like a rise over run, like we had that situation in 2 dimensions. You know, you have 2 points, find the slope, and then a point, you get the equation. That doesn't happen in 3D. In fact, the rise over run really, which is the rate of change, that came up until we got to partial derivatives. So let me get rid of this because I might need more space. Maybe not. Well, anyway. So first of all, we need to define the point. Let's call this P and let's call this Q. So the vector PQ, which is the vector in which the line will be in the direction containing those 2 points. So that is in final minus initial. 3 minus 2, that's a 1. 2 minus 5, that's a negative 3. And 0 minus 1, that's a negative 1. And well, what are we going to do with this? So number one, this represents the A, the B, and the C from the set of parametric equations. But we also call this the delta x, the delta y, and the delta z. That is the change in the x direction, the change in the y direction, and the change in the z direction. And well, although there's many ways to parameterize a linear segment, throughout this chapter I will go with what I think it's the easiest one, especially when it comes to evaluating these line integrals. So we don't want to complicate ourselves. When we parameterize these lines, we're using the method that I'm going to show you, which is something that we already did already. Well, it's just going to come back. Most of these integrals are going to be evaluated from 0 to 1. From 0 to 1. How cool is that, isn't it? I mean, instead of evaluating an integral from negative 7 to 15, instead we can just evaluate it from 0 to 1. Whatever it is, evaluate it at 1 and then just write a big 0. That's a really good advantage. So, a parametric equation for a line. So it contains an x component, a y component, and a z component. And well, we multiply the x component of the vector, which is 1, times the variable t plus the value of x in the initial point, which in this case is 2. That's going to give us a t plus 2. And then we do the same for the y equation. That's going to be -3, which is the y component of the vector containing those 2 points, times t plus the initial value in the given of the initial point. In this case is 5. So that's going to give us -3t plus 5. And last but not least, we multiplied the c component of the pq vector, which is -1, times t plus the z component in the initial point, which is 1. That is, that's going to give us -t plus 1. And those are our parametric equations. And if we write it in vector form, because we will need to write this notation as well later. So that's going to be t plus 2, -3, t plus 5, and -t plus 1. Okay. However, since this is a line segment, we need to specify its domain. And well, because in this case we're using the initial point and the final point, well, this is the domain for this function is 0, 2, 1. And you can always test. So plug in 0 on the vector equation. So that plug in 0 plus 2, that's going to be 2. Isn't that the x component or of the initial point? And 0 times -3 plus 5, that's the second component or the y component on the initial point. And 0 times -1, that's 0 plus 1, that's the point, the z component on the initial point. Now do the same with 1. 1 plus 2, isn't that a 3? And then 1 times -3, which is -3 plus 5, isn't that a 2? And last but not least, 1 times -1, that's -1 plus 1, that's a 0. And it's important to check all this because it's going to matter. It's going to mean everything actually when it comes to defining these piecewise defined smooth curves to compute these line integrals. All right, so let's look at another example, a circle of radius 5. Well, so what do we have for a circle of radius 5? So that's a 5, -5. And well, recall the pair of equations the pair of parametric equations that we use to parameterize a circle of radius a. So number 1, this is the result of combining the equation of the circle x squared plus y squared equals some a squared, whatever that number a is. Well, in this case I'm not using r for the radius because we are using the letter r for the vector function. That's so we don't get confused with it, okay? And well, so there's a couple of ways that you can parameterize a circle, and that's going to depend a lot on the direction. So if you parameterize it in this order, a cosine t and a sine t, well, we want a circle of radius a equals to 5. That means this will be the set of parametric equations x of t x of t equals 5 cosine t, and y of t equals 5 sine t. All right, and well, in vector notation, this will be r of t, that's a 5 cosine t, comma 5 sine t. And in this case, well, because we're looking at the whole circle, t is going to be varying between 0 and 2 pi. That to cover the entire circle, right? But in this case, I would make a quick note over here. This is if counterclockwise. counterclockwise direction. All right. However, there's another way to parameterize this same circle. If we go in the same way, if we parameterize r of t, instead, whenever we interchange these functions, instead of we write 5 sine t comma 5 cosine t, that's going to give us the function is going to draw it in the opposite direction, in this case in the clockwise direction. Well, in this case they're not asking us to specifically write the equation one way or the other way, but we can just mention this is clockwise. And well, we did a lot of this back in calculus too. You know, we put this in the graphing calculator in parametric form, and then well, you made sure not to blink at all, so you can see the direction of the points being drawn on the screen. So clockwise and counterclockwise. What's that going to depend on? Well, it depends on the situation that we're working on. All right. So what do we have? A linear segment, circle of radius 5. So let's look finally at a piecewise smooth curve right here. And in this case, this curve, it's comprised of 2 parts. So number 1, this path along the parabola y equals to x squared, and the second path, which is this horizontal segment from the point 2,4 to the point 0,4. All right. Well, again, that's going to take us back to calculus 2 to parameterize well, at least the y equals x squared. For the second part, well, it's going to be very similar to what we did in the first example. So let's label them. Number 1, let's call this a C1, and let's call this a C2. Okay. So when it came to parameterizing rectangular function to turn those into functions of t, so and I'm talking about the function y equals to x squared. So the easiest way to parameterize a rectangular function is to give the independent variable the letter t. In this case, make x equals to t. So this is what we're going to do. C1 of t. This will be the vector valued function, or which is the parametric equation. Well, if x equals to t, so y would be t squared. And then in this case, we need to be very careful with the domain. So we need to state the interval where this parametric equation is being defined. That in this case, it goes from 0 to 2, and you can verify this. So plug in t equals to 0. What are we going to get? 0, 0 squared, which is the point 0, 0, which is the initial point on the parabola. What happens when t equals to 2? Well, the x component, which if we plug in a 2, and then 2 squared, which is 4, isn't that the final point on the parabola? At least for this segment, for this piece of the parabola, it's not the full parabola. So there we got it. All right, C2. So what's C2? That's okay. Number 1, we need to be very careful when parameterizing this one right here, because in some situation, well, at least in this example, I'm going to go from t equals 0 to t equals to 2, and then I'm going to continue from t equals to 2 to t equals to 3. So we will need to make certain adjustments in order to make this work this way. All right. So one thing to notice, number 1, when we move from the point 2,4 to the point 0,4, do you guys notice that there is no change in the y component? Well, that's a freebie. So that's a 4. Now, so since this is a linear segment, again, in this case, we need to look at the displacement in the x direction in the same way that we did over here In the previous example, the displacement in the x direction, the displacement in the y direction, and the displacement in the z direction. All right. So in this case, what would be the displacement in the x direction when we go from the point 2, 4 to the point 0, 4? Negative 2, and that's very important. Direction matters because we're going, check the arrows, we're going in this direction. So yes, it's 2 units, but to the right, to the left. So that means that has to be as negative 2 times t. However, what happens when I'm leaving some space here to figure out a number that will give us the function defined between 2 and 3. So for the initial point, what happens if I plug in 2 over here? So negative 2 times 2, what is negative 2 times 2? Negative 4, but what do I need to add here in order to get a 2? So plus 3. Okay, let's see if 3 works. Okay, so 2 times negative 2, that's negative 4, plus 3, that's going to give me only a negative 1. I need a 2 in this case. So in this case, well, that makes it, okay, negative 2 times 2, that equals to 4, or rather negative 4. Plus what number would I get at positive 2? 6. All right. Now, is this parameterization going to work when t equals to 3? Is that going to take us back to the point 0, 4? Let's find out. Okay, negative 2 times 3, that's negative 6 plus 6. Oh yes, that's a 0. And 4 is simply 4. 0, 4. All right. And well, we have the different paths separately. Now let's write it down together. C of t equals to t in the direction of I plus t squared in the direction of j in the interval 0 to 2. And the second piece, which is negative 2t plus 6 in the direction of I plus 4j in the direction of, the direction of j, that's a 2, 3. Notice, in this case, I have parentheses here for 2 and brackets for the 2 in the previous function. Actually, check this out. It doesn't matter where you put the parentheses, as long as both are not brackets. You can make it a parenthesis here and a bracket over here, and it doesn't matter, because as long as they just connect, and as long as you don't have both points the same or like overlapping points. All right. Okay. That being said, let's move on to the next page and make another summary of integrals. So, okay. What are the integrals that we have studied so far? So number 1, integrals over an interval, which is the integrals that you learned back in Calculus 1 and you use a lot in Calculus 2. That is the integral from a to b of f of x with respect x. And recall that we always evaluate this integral over an interval a, b. Because this is a thing, and if you try to interpret the geometric interpretation of this situation, well, it's a linear segment. It's a one-dimensional segment, therefore related to a single variable function. Then we went to integrals over a plane region. That was Calc 2. Double integral over the region R of f of x, y. And well, without getting into too many details, like, if f of x, y equals to 1, that's area. And if f of x, y is something else, well, that's volume. It doesn't matter. The thing is that these regions, the regions over we evaluated these double integrals were two-dimensional regions. All right? Now, triple integrals. That's integrals over solid regions. Let's call that solid D. And that's a function of f of x, y, z, dv. And again, without getting into too many details, that if f of x, y, z is 1, it's just volume, otherwise it's mass, you know. Well, I already mentioned, so. And well, let me draw a simple solid. Of course, we can come up with other fancy solid objects. I mean, I guess the cube or the rectangular prism is the one that, and in fact, that's the one we use as the partition to come up with the triple integral using Riemann sums, right? Well, what's a line integral then? Well, I mean, one dimension, this is one dimension, this is two dimension, this is three dimension. Is a line integral 4 dimensions? No, not really. It's not 4 dimensions. So this new type of integral, it's an integral over a curve. And it's similar to, I would like to say it's similar to an integral over an interval, and also over a solid region at the same time, but it's not quite a solid. It's going to be weird here. So, well, the picture is a little weird, but it's going to make sense once we define what it is. So we're going to define this single integral. It's not a double, not a triple, and I'm going to write down a C right below the integral, because that integral is over a curve. It's not over an interval. A to me is not over it's not over a rectangular or a plane region. It's not over a solid, but still that's going to be a function up to variables x, y, ds. And what's s? Remember the s function from chapter 14 or 15? No, 14. Exactly, parameterization by arc length. So s is the arc length. All right. Yes, I mean a lot of symbols, and yes, bringing back some ideas about the arc length function. But ultimately, what's the geometric interpretation? So here it is what we have. So here we have some surface z equals f of x, y. So that's a function of two variables. That gives us a solid region. However, in the solid region, you can trace your favorite, your favorite line, your favorite path. For example, when you're hiking, on again, let me get back to the hiking problem. So, okay, let me actually draw the hill maybe that looks like this. So, this is the hill right here. You have put some trees, for example. All right, and so there's many ways you can hike that hill. You can do it along this curve, for example. I mean, you can just go up the hill. And another way is maybe do this, maybe. Why not? That's another way, right? Or maybe, I don't know, in diagonal like this. I mean, without even going all the way up, that doesn't matter. However, the result that we would be obtaining is, so again, this is solid, right? It doesn't really look like solid. Let me see if I can make it solid somehow. Okay, it looks like it. And that's kind of solid, sort of. Well, so this curve I just draw here, it's going to create some area below. But I mean, isn't it the same as the area under the curve from Calc 1? No, it's not. So you can think of this curve here. Well, in this case, it's actually it's straight. However, if the ceiling of the room were circular, we would have a curve looking like this, right? Sort of. So in this case, that line integral would be the area of this curve under the circular path going along the surface. It's kind of weird, isn't it? And well, we have the picture which is right next to, I mean, that's to get the partition and come up with the idea of that area right here, which is that's the height of the function, which is f of x sub I. Let's call it f of x sub I, y sub I, times delta s sub I. That is this increment in the length of the path, in the arc length. Right? It's just a portion of the arc length, and of course the idea is to add infinitely many of these rectangles that they give rise to. Let me see if I can do something like this. Well, so here we have like let's imagine an upper hemisphere or something like that, or some surface. So if that surface is going to create this, this sort of circular path, or we can also, depending on how do we find that parametric form over the surface, it could be twisted like this. All right, so that's really the area that we're finding. We're finding the area under the path and not under the curve, really. All right, I mean, technically the path is a curve, but I mean, the thing is, we're going to refer to a curve this time as a path. So if we add infinitely many of this f of x, y, delta s of I, so that's really adding infinitely many of this. It's going to give us the integral that we define above. All right, and well, so in this case we're going to need to have a lot of parametrizations. The first example that we're going to do is an integral, like the easy case in which we have our parametric equation as the arc length parameter, and then we're going to define, or we're going to say what do we do in a situation in which we don't have the arc length parameter, and in fact that's what we're going to do for the rest of the section. In the meantime, let's have a look at one of those examples. So we have this surface. So this is f of x, y equals x squared plus y squared. All right. So in solid, I think this is an elliptic paraboloid. If I'm not mistaken, I think it extends horizontally more than it extends vertical. I mean, it extends more in the y direction than it extends in the x direction. And it's going to go along the unit circle, the circle of radius 1. So we are going to plot the unit circle like overlapping on the surface. However, another way to think of this, so suppose this is gonna drop a curtain here. So we're gonna find the area of the entire circular curtain below the unit circle that intersects the paraboloid in this case. All right. Well, so number one, let's evaluate the integral. The integral of c over c of x squared plus 2 y squared ds, where number one, in this case, this is x, this is y. All we do is substitute the x wherever you see the letter x, and the y wherever you see the letter y. And that's all we're going to do for this simple example. So that's going to be, in this case, well, since we know we are integrating over the unit or the unit circle, that means we're going to integrate from 0 to 1, and the quantity x squared, where this is cosine squared of s, plus 2 times sine squared s ds, 0 to 2 pi actually. All right. Well, this is just a Calc 1 integral, maybe sort of a Calc 2 integral, sort of. Well, so let's find a way to integrate this one. Well, notice we have cosine squared plus 2 sine squared. If we had cosine squared plus sine squared, that would have been 1. We can make that happen somehow. Well, how about write this madness like cosine squared s plus sine s, sine squared s, oh come on, sine squared s plus another sine squared s. This is equal to 1 plus sine squared, isn't it? Well, at least it will simplify something. And that's the integral from 0 to 2 pi. And that's 1 plus sine squared s ds. Well, no, this is really a Calc 2 integral because we have the integral of sine squared. Well, we wish we had a factor of cosine so that we can use a u substitution. However, it's not the case. And we will have to go about the power reduction formula for sine squared, which that's going to be the integral from 0 to 2 pi. That's 1 plus 1/2, or rather 1 minus sine s, or sine 2s, over 2 ds. And well, if we split this term, that's going to give us a 1 plus 1/2. That's the integral from 0 to 2 pi of 3/2, and minus 1/2 sine 2s ds. All right. If we integrate this function, we should get the integral, or not the integral, rather, that's 3/2 of s minus 1/4, or rather, oh, actually, that's supposed to be a cosine, right? On the identity. I made a silly mistake. Let me fix it. And that's sine here, sine 2s. Evaluated from 0 to 2 pi, and after evaluating this, we should get as a final answer a 3 pi. So that's the area of the curtain created by that unit circle when intersecting this parabolic surface. All right. Well, it's not it's an elliptic parabolic surface. All right.